In this session, we're going to go into the analysis control part of things. So there's a number of routines that I have prepared earlier again that I use for running the models. You'll see these routines are quite useful. Um, I'll just copy that straight in here. So what these do is they remember right at the start we put in some flags to do elastic analyses, to do runs without solving, to do runs without plotting. So all this does is instead of calling solve or step, um, you'll call this routine smart solve and smart plot. And what those will do is they will check then for you if flag do not solve is not equal to okay, this is obviously old parlance, so I think the flags names have changed. If yeah, just make sure that's right. So if flag solve, then go to the command, solve, end command. So this is actually not something we're going to use because we're not going to use solving very much because what we want to do is apply a load. We could do some solving. It could also be part of this, a number of options for how to approach the problem that we've chosen. I'm just adding to that, if flag solve, then solve. Otherwise, just step for the test steps. And I mentioned that when I introduced that. So, in addition, I've got smart plot. If flag did not plot, again, the flag name has changed. And also, it's now Boolean rather than a 1 or a 0. So, all I have to do is say if flag plot, do plots. So, it'll then call this routine. Now you'll see interestingly here, I've got things like report APS, write APS. This is one of the important things we're going to have to sort out, of course, because at the end of the day, what we want to see is how our pillar is failing, what's going on in terms of the plastic strain. We've already sorted that out with the plot files, but we also want to see what the relationship is between deformation and stress within the pillar. And to do that, we're reporting the average pillar stress. There's a number of different ways of doing this. I want to try and use the history method, which I haven't used before. If it doesn't work out, I can always fall back on this stuff here, which is already written. Okay, what's left? The run manager. So this is the final thing you run, and it actually runs the problem. So there's a lot of unnecessary stuff here. You can see there I had some stuff to apply initial stresses. I can always put that back later on. And basically this is all based around a loop. I do uh, loop over a variable called iStage up to n stages, which is 100 stages. There's the stage name I mentioned earlier. Stage name is vload plus string iStage. So it'll be vload1, vload2, vload3, etc., etc., etc. And then I cycle for a certain number of steps. Plot counter equals plot counter plus number of steps per stage if plot counter is greater than plot frequency. Oh, so you can, this routine is designed so that you don't necessarily output at the end of every stage. You have a counter which determines whether or not you do a plot. So you can independently run X number of stages and do plots whenever you like, basically. So if I look, plot frequency equals, yeah, when you see the word hack as a comment, it's probably not very well coded. So it's probably more sensible to just exclude all of that. I'm again going to comment it all out. And again, this, not sure if I've mentioned this before, but this function of using Alt and Shift to select diagonal pieces, extract outputs. Okay, that's part of the APS reporting, I think. Final save is then file root plus final save. So you remember there's a do I save or a flag save. I'm actually going to ignore that for now because I don't want to save along the way. I just want to save at the end of the problem in case I want to do something else to it. So let's, yeah, so this should run fine. Max n steps per stage. So total steps 80,000. I'm going to run it over 80,000 steps over 100 stages, and that'll give me X number of steps per stage. And then I'm actually going to just smart plot after I've done the run. Nice and simple. Okay, this thing doesn't exist yet because I haven't called in the data file that contains that. All right, so this will work. It'll give us plot files every so often. It won't give us anything. It won't give us a APS plot. So to do that, I know there's a call somewhere in this call process pillar.fis. Let me bring that up. You could just type in here and it'll fill it in for you. Process pillar.fis. Open. Yeah, it's one of the first files that was opened here. So let me bring it right to the end where I'm working. Okay. It's a fairly complex piece of code, probably unnecessarily so. There might be a much simpler way of doing this using histories, but I'm going to look that up now. So I know that I can't just output a known variable. I'm going to have to do a calculation to work out APS. I'm going to have to take all the. There's two ways of doing it. You can either add all the unbalanced forces together, or you can of the grid points and average those over the area. It's just easier to it's easier to just capture the stresses in the elements or the zones along that central plane. And to do that, and then extract sigma 3 or the vertical stress. So I know I need a history. I know I can't use normal zone histories, and I was secretly looking here while not being recorded. So if I look at zone history, you see there's a huge selection of things that are available here, but average pillar stress is not one of them. So to do that, I'm going to have to run a function. So under the fish command, again, this bit of workflow in terms of using the manual. Usually you start looking at the zone. Yes, zone history is there, but that's for zone and grid point values. I need an output that's going to depend on a function. It's going to be the output of a function. So fish history, create a history of the fish variable, whatever that symbol happens to be. Oops, let me go back, that's not very useful. A name can be assigned, blah, 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 blah. The value of the history will be taken at the history interval. The return value is assumed to be a number. The value of the history will be taken at the history interval. So the history interval is every 10 steps or so. It creates a history plot. The return value is assumed to be a number. So it's not clear to me from this. You see, if I have a symbol, so I can say, hey, call it APS, whatever, and I have a routine that's there for calculating that APS value, but I don't know whether it's going to um, automatically call the variable or not, and I'm going to have to do a bit of a search on that. And here's another useful part of the workflow. So I'm not clear from the documentation exactly how this thing works. This is pretty vague. So what I'm going to do is again use a useful function within Notepad++. Text, yes, Notepad++. You'll see here under the file window, the find window, there's find in file. So that's very useful. So what I'm looking for is fish history. I don't want to replace it with anything. I want to look in all these types of files. And you'll see here I've pointed it at the data files that are shipped with FLAC 3D version 6 or probably version 7 too. So, and I've clicked there all, look in all subfolders as well. I just run a find. Now what I'm trying to do, sorry, excuse me, what I'm trying to do is find examples. So let's see if there are any examples in the existing files, and it looks like there are. Okay, triaxial compression, more Coulomb. I just double click on that and it opens the file for me. File history HHQQ. So fish define. Okay, it's one of these. So this is how you set this up. You will do a fish define. You'll give the routine a certain name. Let's call it APS. And then at some point at the end of that file, you will assign that same name as the fish routine to a variable. And that will then be the variable that's output to the history. So that makes it a lot simpler. Okay, going back here, just got to think about how I'm going to set this up. I'm not going to create a subroutine. I don't think I'll do it all in here. Yeah, okay. So I know I'm going to have to call it fish define output APS. And I'm going to obsessively put my little colons, semicolons everywhere. Okay, so what do I need to do? Let me check this old routine. What do I need to tell this routine so that what I'm going to do is I'm not going to mess around with unbalanced forces on the grid points. I'm actually going to extract it from the zones themselves, the stress values from the zones themselves. So looking at the model, I said I think there were 10 high. 2, 3, 4, 5, 6, 7, 8, 9, 10. So in that case, there's actually no, it's an even number, so there's no center line. So I actually have to look then at both of these rows of elements and average across those to get the center pillar APS. I can change that hopefully simply by dividing by 11 instead of 10. Hopefully that's here. There we go. Zone size will be the mining height over 11. Now I'll have a central zone. Now this APS routine needs to know where to look. And I can actually do this in a number of ways again. In fact, what I'm going to do is do fish define setup APS end, because again I don't want to, this thing is going to be, this output APS is basically going to be called every history number of steps. So every 10 steps it's going to call that routine and run through every instruction there. I don't want to have to go and work stuff out again that I only need to work out once. Now one of the options would be for me to search. I'm going to have to search through all the zones. I'm going to have to use a loop for each over all of the zones. But what criterion am I going to use to say, okay, I found one of the zones that lies in that center plane? I could say, okay, its position is between such and such and such and such. But remember, the thing is going to be deformed. So So really, I could end up then having an APS working perfectly and suddenly with that zone exiting my search area and then being gone entirely. Another option is actually, because I know where all the zones are, I mean, I created them, right? I know how many there are in X and Y and Z, etc., etc. I could just say, okay, from this, I could loop over all the points or the centroids of all of those zones and say, okay, give me GP. I can use the Z near zone. It used to be called Z underscore near. Now it's called zone dot near, and that'll give me the nearest zone, and I will cover all the zones in that way. The most elegant way of doing this probably though is to use a group. So I will search over all the zones again, and I will only include zones within a particular group. So in the setup APS, all I will do is assign that particular, is assign a group, and then I will use that later when it comes to the output APS. Right, so As I mentioned in the lecture, zones are ranges are dynamic. So every time I access this range, it'll change whatever's in it, um, unless it's referring to a group, of course. A group is a persistent set of entities, so I'm going to approach it from that perspective. All right, so how do I create a group? Um, well, firstly, how am I going to define the group? At the very start of the model, I know exactly where everything is, so I don't have to worry about things moving out of place. So I will just specify a Z range, and I know exactly what it is because I've specified an uneven number. Now, um, I will say everything with a centroid between 1/2 zone size below and 1/2 zone size above. So it'll be a Z range. And let me just check what variable names I've used. I know I've got the word zone size here somewhere. Zone size, that's correct. And the center line of the pillar is at Z, Z naught, yeah. So Z naught plus, Z naught minus, okay. So I'll say APSZ high equals Z naught plus, oopsie, zone size. In fact, you know what, I'm just going to leave it at zone size because what if I do use an even number? If I use an odd number, it probably, hopefully won't get to the next zone. If I use an even number, it'll work fine. So, well, let's try it anyway. Because it will assign this group, we can check it very easily. APSZ low, Z naught minus the zone size. Lekker. Okay. So then all I do is command. I'm going to use a command, a flat command to specify the group. I could do this in Fish if I really felt like, but that's built in, so let's use it. So can't remember the syntax, so let's see if we can do it this way. It's going to refer to zones, so I go to, let me collapse this so we can see my workflow a bit better. I've got Flax 3D elements, zone, it'll probably be zone group, hey? Zone group command. Zone group, S is name, keyword, zone group slot name equals group name, what? Okay. So I'm going to use a different slot now because this is this is going to overlap with the groups I have in the default since I have the entire coal pillar included in as one of the groups. So apologies again. Let me say zone group name slot range. So it should look like this. Zone group uh, APS slice slot APS range, and I'm sure I've used range here somewhere. Range zpos. I'll just copy what I used for the, yeah, here we go. Range position Z. And I may have rabbited on about this earlier as well. How if you use two values, it's between those two values. So APS Z low and APS Z high. Zone group APS slice slot APS range position Z blah blah blah. Okay, so I suspect that's all I need to do. Remember as well, I also need to work out the compression. So my pillar compression, what I'll do is I'll determine the difference between these and average them. Okay, let me think. So I'm not going to do anything fancy. I'm just going to say, okay, this is my, sorry, let me just see the axis again. Not that it matters, but I'm going to say X, oopsie, excuse me. So compression X high equals, oh wait, I think I'm going to use the pointers. So we talked about pointers earlier. Pointers directly point to, no, I'm not going to use pointers because, yes I am, sorry. I'm going to use pointers because I'm going to work out the compression. So I'm not going to use history points. I'm not going to take the history of that particular point. I'm going to calculate under the output APS thing. I'm going to do two histories, output APS and output compression. So I'm going to get pointer X high is, so that is going back to my sketch. Oopsie. No, that's not what I wanted. Let's keep your sketch open. So in terms of X, that was just called XP equals, so I'm going to use this function here, gp.near, and I think that's under zone as well. Sorry, but it's not a command, it's a fish function. Now you'll find all the grid point commands are actually under zone, useful to know. gp.near, so the pointer to the grid plot closest to V, and that'll be XYZ, yeah. That's gp.near and it's just XYZ. So the X coordinate we know is XP, the Y coordinate is, sorry, Z coordinate is ZR and Z floor. That'll be Y naught and Z roof, right? There we go. Okay. Pointer X low. Whoopsie, somebody. X low, GP near will just be the same for Z floor. And again, I'm just going to cheat by putting that as Y. These will then be X naught. And these will be P. There we go. Easily done. All right. Okay. So now I've got that information. I'm going to run the output APS thing. All right. So to get the APS, I need to loop over all variables in the problem. I'm going to need some additional variables. I'm going to need a running total of APS. And I'm going to need a N APS zones. So this is going to be 0 to start with, and this is going to be 0. I'm going to take an average, so I'm going to add them all together and then divide by the total number. All right, so loop for each zone dot, is it zone dot list? All right, let me check this. Control, sorry, Control F. See, loop for each Z pointer zone list. Okay, there we go. Let's copy that. That loops over every zone in the problem. Always useful to just end your loop so you don't end up in a situation where you don't know where you are. So this Z pointer will then refer to whatever the zone is. So pointer, let me just undo whatever changes I made here. So and you can see here there's a search going on before I knew how AND worked. And for each one I'm just going to say if, I think it's zone.group, and I'm just going to check the syntax here. Zone group EFG. There we go. If zone group Z and slot. Oh wait, is there an is group? I think there's a command called is group rather, which returns a. There we go. Zone is group. So it'll return a boolean, which will tell me true or false. Basically, it's a test for whether the thing is in this group. So the group will be APS slice, and the slot is APS. So now I know I've got one of the required things. So, do I use Sigma 3 or do I use Sigma Z? I'm going to go with Sigma Z because why not? It's not going to be that different anyway. So zone stress, there's value access, zone stress, zone.stress.zz, pointer, okay. So ZZZ in this particular one, and the reason I'm spreading it out rather than adding it straight away is for debugging purposes. So this ZZ equals zone.stress.szz, I think it was. Zones.stress.zz, obviously I don't need the S. And the only argument is the pointer, I hope. Yeah, pointer, there we go. And you see there's something wrong with my syntax up here. You can use this back, which is useful. Zone is group Z, then S and slot. So first argument you need, of course, is the pointer, so it knows which zone to look in for these values. And it's S and slot. Okay, I think that's it anyway. All right. This is that. So run total APS equals run total APS plus this ZZ and increment this. The number of zones equals the number of zones plus 1. Good, and that's it. That's the whole routine. Except I need now to output the APS value. Output APS equals running total divided by the number of items in that. Okay, it's a float divided by an integer, so it should all work out. Okay, all right. Now I need one more routine to give me a history of compression. Output comp. So I never actually call these routines. It's going to be the history definition that calls these particular routines. So let me collect what I had earlier. GP near, yeah. So I want to extract the GP. I can use GP pos. If I know the original distance, why not? I can just subtract from the current one, but let me see if GP disp is there. Yeah, there it is. So GP disp dot Z. Okay. So compression in X is simply GP disp Z. GP disp, yeah, GP disp Z. And the arguments is just the grid point. So the top is going to move down. So I want to subtract the bottom from the top. Okay, so it'll be low, pointer x low, minus, same again, but this time x high. Same exactly for y comp, pointer y low. Or is the sign reversed? Could do this using vectors, of course, but it seems a bit excessive. Let me just think about this a second. It's going to move probably downwards as well. Alright, now let's see if it works. Output comp. In fact, you know what? Let me use position. Use position. It's just going to be easier. Well, I have to think about it less, so in that sense, I suppose it's easier. GP pos xz. So I'm going to have the upper one because it's larger. High minus GP pos zx low. So x comp is GP pos z x high, pointer x low. That'll give me the distance. So the initial distance though is will simply be z roof minus z floor minus, I'm just putting brackets for my convenience, they're not necessary, GP pos z. Okay, well, I don't see that that won't work. Well, let's see. If we get a big negative value out, we know we did it wrong. All I need to change is y. Comp equals, oh, I put too many. There we go. I put comp equals x comp plus y comp over 2. There we go. Done. Now we'll set up the histories. And I'll just do that in the command space here. See if it works out. I can't remember the syntax now though. It was fish history symbol. Okay. Yeah, whoopsie. So I just, I've seen people use truncated stuff, but there's no real purpose to that. Not like I'm in a hurry, I'm going to run out of text. And then I'm going to put APS. And I seem to remember that needs an @ symbol. It's a bit of trial and error as to whether something needs the @ symbol or not. I was using, for example, callbacks, which is what while stepping used to be. And that's a bit of a hit and miss as to whether you use that @ symbol or not. All right. Well, should work. Let's run it up and see. not execute setup outputs. Not a function. Okay, that was left over from. Ah, okay. I forgot to run. Ah, sorry. Firstly, I forgot to run this. This is a separate problem I'm discovering now. If I hadn't run, if you don't run this, then it'll never assign that group and it'll never assign those pointers. And all of this will be for nothing. Nothing will happen. You'll just end up reporting zeros. So it said set up something didn't work. Set up outputs. Yeah, okay. These are both routines which aren't actually part of this thing. Let me just check my smart plot as well. There we go. Again, things it's not going to recognize. Oopsie. Okay, let's try it again. And it's running. Okay, so I'm going to create a new plot file. And you see it's set up. It uses all three. Okay, so I need to reduce that by half probably, but what I'm going to do anyway, just to make sure everything's running. History chart, and you'll see here there's three values available, the mechanical ratio limit, which is not very useful now because we're not actually solving for anything. So I'll get rid of that. The APS, which is plotting along nicely. And I'll get rid of that because it's not going to be in the same scale. And the compression, which is also working nicely, I think. All right, we can test this all in a bit. Just going to let this run for a bit, and that'll be our next session.